Hello, I'm Simon Judd and I'm going to be talking about membrane bioreactors from the perspective of both the academic profession and the people that actually use the technology, who tend to have fairly specific concerns. If we look at the research trends since the year 2000, and in this graph here, the y-axis is a representation of the relative frequency of the outputs, then it's fairly evident that the main topic of research in MBRs is surface fouling. Now, notwithstanding the vast amount of research into fouling, the reality is that in practice, surface fouling, at least in municipal MBRs, has only a small impact on the overall costs and also doesn't present a significant challenge to operation either. A few other trends are also fairly predictable in this plot. Research into nitrification and or denitrification has probably bottomed out. Same applies to phosphorus. Of course, both phosphorus and nitrate represent nutrients, which is a hugely important topic. Anaerobic MBR research, on the other hand, has steadily increased, reflecting the focus on sustainability overall. And for the same reason, research focused on energy has also steadily increased, though the proportion of papers on energy is still pretty low. But when it comes to publications on what could be regarded as practitioner relevant topics, such as cost, well, the numbers are very low, less than 2%. For membrane channel clogging, which is a pretty widespread challenge in municipal MBRs, just a handful of papers. And it's the same story for integrity impacts on disinfection performance, a massively important topic in water reuse, but hardly any research. But the actual total number of research papers on MBRs is still increasing quite steadily. Well, I'm pretty sure most people listening to this will be asking the same question: what's clogging? Well, this is an example of progressive clogging of a flat sheet channel in a bench scale test, but rest assured, it happens in full scale plants too. If we look at the causes of permeability decline on an MBR, then there are fundamentally two different causes: fouling of the surface of the membrane by colloidal and macromolecular organics, and clogging through solids agglomeration. Fouling can be removed either physically or only by using chemicals, respectively designated reversible and irreversible fouling. Clogging can also be subcategorized as either sludging, which is the filling of membrane channels with solids, which have been widely observed both for flat sheet and hollow fibre configurations, and the curious phenomenon of ragging or braiding, which is when long lengths of material are formed from some component of the solids. And when you see ragging, it looks as if someone has thrown several meters of rope into the membrane tank. But in fact, these rags you can see here are formed from agglomerated solids, exactly as with sludging. It's just that it looks pretty weird. So is it even worth looking at clogging? Well, in practice, membrane permeability for an immersed MBR is sustained by air scouring and backflushing, which mainly dislodge the solids from the membrane surface, and chemical cleaning, which is aimed to remove whatever's left after the physical clean, and that's going to be mainly dissolved and colloidal organic carbon. Now, these cleaning protocols clean the membrane surface. They don't affect the membrane channels or any other part of the membrane module at all. So if the channels become filled, or those rags form and wrap themselves around the module or the aerators, the only way of addressing this is by removing the membrane from the tank and cleaning the solids away manually. And that's not very popular. So the next question is, are clogging and fouling related? Well, apparently not. Sludging seems to relate more to the sludge rheology. In this graphic here, for two different sludges, each at two different concentrations, the sludges have been characterized according to their apparent viscosity, their capillary suction time, which is an established simple measurement of waterability, their soluble COD content, which loosely relates to fouling propensity, the measured sludging propensity at low shear, and also just one datum at high shear. So, according to this data, the clogging, that's the green bars there, increases with increasing viscosity and CST. The fouling propensity, on the other hand, doesn't follow the same trend at all. It perhaps relates to soluble COD, if you look at those two sets of bars there at the end, but not to sludge viscosity. Ragging, on the other hand, seems to relate to the cotton wool content specifically. And this is a simple demonstration of ragging in action. I'll just switch this on now. Where you can see there, those little white bits there, they're basically individual strands of cotton wool which are being stirred in a large tank at a very low concentration, no more than 5 milligrams per litre. And what happens after about 1 to 3 days is that those single lengths of cotton wool agglomerate to form a single lump or rag. And that rag is mechanically strong enough to be fished out as a single rag. Try it for yourself sometime, it's great fun. So the bottom line is that neither sludging nor ragging are fouling related. So all those EPS measurements are of no use at all in clogging propensity measurement. So what about integrity? And why is it so important? Integrity reflects the breaching or damage to the membranes, which means that pathogens can break through them. That becomes critically important in water reuse, where credits are assigned by the regulators based on the expected pathogen rejection, where the credit is simply the log of the feed to the permeate concentration. Well, that's all very well and good, but most of the time the permeate concentration is below the limit of detection of the instrument, provided the membrane isn't breached. So, in reality, the LRV is given by the feed pathogen concentration, the limit of detection of the analytical method used, and the frequency of breaching. So if you wanted to increase the credit from, say, 2 to 3, then you just increase the limit of detection of the analytical instrument by an order of magnitude. But if you could also guarantee that the membrane is never breached, then the LRV value would always be infinite. Infinite credit. Now that would look good on a degree certificate. And now, on to the thing that matters most in life. Money. There's been a few sets of capital cost data presented in the past few years, and here they've been normalised against the flow and focused on fairly small installations for this particular plot. This includes one set from Spain, one computed from the CapDet works function within Hydromantis, and some data from Japan as well. And these give an average pretty close to the CapDet works curve, which then also asymptotes to within the range of values published for large MBRs. The easiest way of assessing the total cost is by calculating the present value, PV, in millions of dollars. Here's the CapEx curve, calculated from the data given in the previous slide, and this is the OPEX, giving the total PV. What's interesting though is the contribution from the labour costs to the OPEX. And if we just focus in on this aspect and look at the OPEX per metre cubed, that's on the Y2 axis there, you can see that the labour cost becomes increasingly significant at smaller flows. The data for the largest flow capacity are otherwise in reasonable agreement with the published data. But what actually determines the labour costs? Again, not a huge amount of research in this area, but clearly the geographical region is going to be influential in terms of the staff rate. But then there's the amount of effort. Now again, this is very hard to pin down, but there's an interesting set of data presented recently which came directly from the UK water utilities operating potable water membrane filtration plants. The data could be divided into routine and non-routine or reactive labour. And it's worth looking at this data more closely. As before, the specific OPEX in pounds per metre cube this time decreases with flow capacity. And there's actually an impact from the selected membrane technology on that trend as well. But most interestingly, the reactive labour effort is roughly 50% of the total effort at all flows. The cost of reactive labour is likely to be more than 50% because reacting to something you weren't expecting always costs more than routine scheduled maintenance because you have to pay the people more to react to something which you weren't expecting. But what demands non-routine effort? Mainly membrane repair for potable applications, clogging for both potable and wastewater applications, and foaming in biological wastewater treatment. So, I refer you to my previous point. It's worth knowing something about these particular phenomena. So, in conclusion then, here's just 3 points about the direction of travel in MBR R&D. Process upset frequency and the subsequent impact on cost is pretty important. Industry actually employs something called FEMIA analysis, that's failure mode and effect analysis, to try and figure out the impact of process failure. This is mainly to assess product water quality and flow impacts. It rarely encompasses cost. Costs are looked at, but only from an optioneering perspective. Membrane integrity is an area where it can definitely be said we need more research, the favourite phrase of any academic researcher. The fact is, if there was any kind of quantitative causal relationship between membrane integrity failure and any aspect of design and/or operation, then we would be significantly better informed than we are currently. Maybe kick off with a comparison between ceramic and polymeric membrane modules, just for starters. And all this feeds into regulation, because risk-based parameters for process failure are bound to be more relevant than a notional LRV for assigning those credits. Thank you very much.